A short introduction. So, and I'd like to welcome all of you to the last talk of the first season of the optimization online seminar. So it's my pleasure to introduce Coralia Carțiș from the University of Oxford, so who agreed to give this talk. So, I mean, I just want to say that yeah, I mean, it's not good to speak about ages. But I like to say that I met Coralia the first time, let me see, 26 years ago, in the first seminar. Yeah, I think it was algebra, I guess.
Yeah.
In the bachelor program at the University of Cluj-Napoca in Romania. And yeah, so Coralia, thank you for agreeing to talk in the seminar. So yeah, it's a great opportunity to meet here again. Of course, we met also in the past, yeah? But yeah, let us do it also in this way in an online seminar. So the stage is yours, Coralia.
Thank you very much. Thank you very much, Radu, for this initiative that you have started and for this invitation. I'm sending greetings to everyone from the Mathematical Institute, where for better or worse, we are reopening. And I would like to talk today about the tensor methods for non-convex optimization problems. And I would like to acknowledge my long-term collaborators and friends, Nick Gould and Philippe Toin. And let me begin with setting the framework. So most of this talk, for simplicity, is on unconstrained optimization, though we do know some things about constraints as well. So we want to minimize a function that's smooth, and to set notation, I'm going to denote derivatives in this way. And we are looking to find local minimizers using derivative-based methods. So starting from an arbitrary guess x0, we are going to generate iterates xk. And at every iterate xk, we are going to approximate our complicated function f by a simple model of f that's a linear or quadratic Taylor model to begin with. And then instead of minimizing the complicated function f, we are going to approximately minimize this simple model to generate a change to the current iterate. So to generate sk, that will then be used to update the iterates, and we will terminate within epsilon of, say, small gradient value. So this is a simple framework where here's the a linear model that gives rise to steepest descent directions, or a second order model that gives rise to Newton-like directions. But if we just minimize these local models and use these steps to generate the iterates without any other ingredient, we wouldn't get a globally convergent method from an arbitrary starting point. And so we need some safeguarding strategies like line search, Russ region, or regularization that essentially constrain the step and check its length with respect to some decrease in the function, so as to ensure a sufficient amount of progress per iteration. What is my talk today about is about complexity of derivative-based optimization methods and global, so in other words, global rates of convergence. So from an arbitrary starting point, we want to find out how long will the method take. And I would like to start from this maybe surprising fact that when you look globally at methods for non-convex optimization, methods that are fast locally, like Newton method, look as poor as steepest descent, as slow as steepest descent. Here's an example of a function that's sufficiently smooth, that has Lipschitz continuous gradient and Hessian globally, but that takes epsilon minus 2 iterations to generate a small gradient, so gradient below epsilon for f. And this is by applying Newton's method. and epsilon minus 2 is the same as the complexity of steepest descent, and so this is kind of disappointing. So starting from this fact, we want to understand, I want to first just summarize what we know about standard methods, about regularization methods, and then I will go on to talking about higher order, going beyond second derivatives. Okay, so here's a table of complexity bounds for first and second order methods when f is non-convex. So under Lipschitz continuity assumptions of the gradient and the Hessian, one can guarantee that the gradient is below some epsilon 1 tolerance and has a sufficiently non-negative definite Hessian in at most this many iterations. So you can see here steepest descent is epsilon 1 to minus 2. Cannot guarantee anything, of course, about second order. Newton globalized with line search or trust region methods, in a classical way. Also that has the same complexity as per the previous example for first order, and has epsilon to minus 3 for second order. And then we go on to cubic regularization methods, which have better complexity to first order. And then there were variants of trust region and line search that were proposed that try to mimic the good ingredients of the cubic regularization complexity to ensure those kind of bounds for trust region and line search variants. You can notice here that to second order, this distinction between methods kind of disappears. But to first order, regularization and these enhanced trust region and line search variants are better. The big O notation hides distance to the solution in the function space, hides, so this gap, the optimality gap, and hides various Lipschitz constants and some algorithm parameters. The other thing to say is that these bounds, though they seem, and they are very pessimistic, they are actually sharp, and that in fact there are optimality results from a complexity point of view for cubic regularization frameworks when you look at these methods in comparison with other second order variants. So this epsilon to minus 3/2 bound is actually optimal for second order methods applied to non-convex objectives. So I want to now describe the regularization framework because all the algorithms in this talk are based on this kind of framework. So I will describe this variant that can be shown to have the epsilon, the optimal complexity for first and second order, and then I will go on to tensor methods. So let's look at it. So what does this approach do? It constructs a local model, a local second order model of the objective, Taylor model, T2 here, regularized by the cubic power of the step and having here an algorithm parameter sigma k, that's a regularization weight. This local model, if the sigma k here was a multiple of the Lipschitz constant of the Hessian, it would always sit above the function, the true function value at the next point, at xk plus s. And so the idea is to minimize this model, which will then force a function decrease. This idea goes back to Grivank, Nesterov, and Poyak. And so this idea of regularizing by the cubic power is crucial here. And then what we do is how accurately do we minimize this potentially non-convex local model? It will be non-convex when the Hessian is not positive semi-definite. What we need to do is just to ensure very simple decrease of the model from the current value of f at xk, so that's the value of the model at 0. And then we need to decrease the gradient of the model sufficiently for some θ1 that we can choose it, whatever we want it to be, and to calculate and to make sure that the point we calculate is also approximately second order critical. But there is no global model minimization required to achieve the good complexity. It's possible for this non-convex model. There are very efficient characterizations that one could use. However, this is not necessary. Just local approximate second order criticality is sufficient. And in fact, if you just want to obtain the first order complexity bound, the optimal bound, just ensuring first order criticality here and the strict decrease, simple decrease, is enough. And then one measures progress in the function at the trial point that we calculated as k, compared to not quite the model decrease, but the decrease in the Taylor series, T2. If this rho is sufficiently positive, then we take the step. Otherwise, we stay at the same point xk, and the only recourse we have is to update the model, namely to increase the regularization parameter, sigma k, and that has the effect of shrinking the step and giving us a better chance of, when we reevaluate rho, of getting a decrease. So it makes the step shorter, the model hopefully more accurate to the Taylor and the true function. We also allow sometimes sigma to decrease in the algorithm so that it does not become unnecessarily large in the run of the algorithm and thus penalizes the step too much. The other thing to notice here is that we never switch the regularization to 0. So there is a sigma mean lower bound on the regularization parameter. And so this method that never takes pure Newton steps. Okay, so this is the core framework here. So now I would like to transition to talking about tensor methods, and what I underlined in red on this slide will be what will change. That's it. The rest will stay the same. So the question we now want to ask is, what if somebody gives me higher order derivatives? Let's assume we are in this amazing situation. So here we are. Assume that that we can construct a local model that uses piece order derivatives. Okay. So we have then the ability to construct a local model that has a tensor, a piece order, a Taylor expansion here of our function, including these derivatives, these piece order tensor derivatives. And then the correct regularization here is by norm of the step to power 2, the 2 norm to power p plus 1. Okay, and then again, we are only going to require approximate minimization. And here we change the right-hand side of the accuracy on the gradient to be to power p, and the accuracy for the second order condition to be to p minus 1. And here we measure progress with respect to TP. That's it. The rest of the framework stays unchanged from second order. All right, so what can we say? Well, if f is, of course, Cp, bounded below, and the piece order derivative, the piece derivative is Lipschitz continuous, then this ARP framework requires at most this many evaluations of f and the derivatives and major iterations of the algorithm to ensure first and second order criticality. Of course, if I only require first order criticality, then this epsilon 2 can be set to infinity, and then we recover the bound in Bergen and Philippe and others. And if we add the second order condition, then we can also characterize second order criticality. So what do we notice about these bounds? Do they improve? Indeed, they improve. they get better and better with growing p, as we would expect. Are these bounds sharp? Yes. And in fact, the first order bound, this minus p plus 1 over p, is actually optimal for p order methods, as shown by Carmon and others. Okay. What are the key ingredients of the success in the complexity of these methods? So I will now attempt a sketch of proof. Okay, just before everybody goes on holiday, let's keep our brains working. So there are two ingredients that are true for second order and then were generalized to higher order. So they started with, with ARq and Urey's, Nesterov and Poyak's cubic regularization. Sufficient decrease. So on every iteration where I take the step, then from the expression of rho, we have this relation here that the function decrease is a multiple of the model decrease. The Taylor decrease. And so instead of TP here, we add the model, the regularized model, the piece order regularized model. And the only difference between the Taylor and the model is this regularization term, okay? But we imposed that we have strict decrease in the model. So this f minus m at sk is non-negative. And so this whole right-hand side here is greater than a multiple of norm of s to p plus 1. Okay? And remember I said that sigma k is lower bounded by sigma min, that we never, by some user chosen constant. It can be anything. So we never go below this regularization value. And so we have here a decrease in the function that's a multiple of the norm of the step to p plus 1. Okay, this expression in red I will not explain yet. So the next ingredient then is to lower bound the step, the length of the step. And the advantage of the improved complexity of these methods comes from long steps. Globally and asymptotically, one is able to take longer steps. And so what we do is using Taylor and Lipschitz continuity properties applied to Taylor series, Taylor polynomials, we can show this lower bound on the step. So for first order, the norm of the step is a multiple, sorry, this should be norm. Sorry, this should be norm of the gradient here. Is a multiple of the norm of the gradient at the next point to power 1 over p, and to this should be minus lambda min, sorry, I have some typos here, to 1 over p minus 1 for second order. So this comes from Lipschitz continuity properties and expanding at the next point. So now, so until termination, so when first order criticality does not hold, then this gradient is above epsilon 1. And so we have this lower bound on the step. And similarly, for the second order, we have this other bound on the step. So the step can be lower bounded by the smallest of these two decreases. And here we are. We go back to the sufficient decrease expression, and we can conclude that we can lower bound by a fixed multiple, the decrease in f. Okay, and here are the key powers that come up into the complexity, these epsilon to these right powers. So now what we do is a telescopic sum. We are going to sum over all successful steps, over all steps, which boils down to just giving us something on the successful steps. On the left-hand side, we have a bounded term by the optimality gap, and on the right-hand side, we have the number of steps times this constant decrease. And so the complexity is essentially the reciprocal of this right-hand side on the function decrease. Of course, we also have to relate successful to to know how many unsuccessful steps we had. So iterations where we didn't make any progress because we didn't take the step, but that can be done easily through the mechanisms of increasing and decreasing the regularization parameter. So it's rather simple and straightforward. Okay, can we go beyond second order criticality? So what are the conditions, first of all, for second order criticality? So for first order, we have zero gradient.
Cora, we have a question.
Yeah.
So why it is not max?
In the last slide, you deduced that the normal S is greater than the both of the two. So why is not max rather than mean?
Okay, because I don't know, there are iterations where one of the conditions will be violated, but not the other. So there will be iterations when the gradient is above epsilon, but not the Hessian, and vice versa.
Okay.
So I cannot, and iterations where both of them will happen. So, and we calculate the step. So on every iteration, we calculate the step to guarantee the condition in the model for both of them. So we cannot really, maybe it's possible to do another analysis where one decouples these conditions. So you say, well, I'm just going to do a first order step. But the other issue here is that it's the gradient at the next point. You see, so I don't know how to do a decoupled analysis to have the max there because of the following fact. Let's say you're in the algorithm, then what are you going to say? If the gradient at this point, at the current iterate, is above epsilon, then I take that step. But here, this property is for the gradient at the next step. So I cannot say that in the model I'm going to take advantage of this and only do a first order or a second order step, depending on which condition is violated.
Okay, thank you.
Okay, so let's go now to third order criticality. So what is the third order criticality condition? So it's telling us, of course, okay, let me backtrack a little bit. So assume you terminate. If the Hessian at the final iterate is positive definite, then that's it. You have a strict minimizer and you're done. If the Hessian is indefinite, or it has very approximately small eigenvalues, so approximately indefinite, because we are ensuring that the smallest eigenvalue is above minus epsilon 2. But if you have eigenvalues that are in absolute value less than epsilon 2, then you want to guarantee that the third order derivative is also small along those directions, along the corresponding eigenvectors, basically. So the third order tensor is, if you were to consider absolute conditions, is 0 on the eigenvectors corresponding to 0 eigenvalues of the Hessian. That's the pure third order criticality. And we make this condition approximate, and we say that we want the third order tensor to be small along directions that correspond to approximately small eigenvalues of F. So in addition to first and second order criticality conditions. Why would we care about this? Well, we care because if we have higher derivatives, surely we should be able to maybe guarantee higher order criticality. There was a question. I thought there was a question, but I can't see it.
No, no question. No.
Okay. Okay. So take the previous ARqp framework, and what we can do is to, of course, we need to minimize the model to a similar kind of condition. So we need to find approximate third order critical points in the model. And so we require that we do that. So the third order tensor has to be sufficiently minimized along directions that correspond to sufficiently small eigenvalues of the Hessian of the model. So if you add this to the other first and second order conditions for the model, then one can show this complexity to third order that can guarantee an approximate third-order criticality for the function. There are some details here that the set for which we guarantee this is corresponds to the directions of the Hessian for the model, which contain directions on which the Hessian is also small, but they may not be coinciding. We can improve on that if one is willing to do more accurate model minimization. So instead of having powers of the step here, one has solves to epsilon accuracy. But it's still an approximate third order condition. Okay, now can we do better than third order criticality? We have a Pth order model. We have a derivative information about the function up to order P. So can we go beyond third order? The first question is, what are higher order optimality conditions for a non-convex function? Okay, horror, all right? So they are not going to look pleasant. You can find more details in a paper. And I will give credit to Philippe when he was here on a sabbatical where he spent a lot of time looking at these derivatives. We have a local minimizer of f, and f is, let's say, CQ. So Q is going to denote from now on the criticality order, and P is going to be the order of the model. So what one can do to derive optimality conditions is to look at feasible paths at curves along which Taylor curves, polynomial curves along which f could decrease. Of course, we know that even if there is no decrease along such paths, it does not. They may not be sufficient conditions for a minimizer because the function may still decrease for non-algebraic paths, and these are these famous examples of Hancock and Peano, where one gets when f decreases along non-Taylor arcs. However, in this framework, we assume that we assume that for sufficiency, f only decreases along such arcs. But no matter what, this is a necessary condition for optimality. So if you have a local minimizer, then the function won't decrease along such arcs. It cannot decrease along such arcs. And then if you look at, okay, I want my function along such arcs not to go down, then you can prove this kind of conditions, that if you fix J from 1 to Q, then you have to have this non-negativity for various index sets in index in PJK. So all derivatives up to order J will remain in the sum non-negative once you are in the kernels of lower order derivatives. All right, so this looks very involved. One can use these conditions to derive standard first, second, and third order conditions. So they will be, you can recover them by choosing various directions S. We can incorporate convex constraints, and we do in the paper. And the advantage of first, second, and third order is that they can be completely, essentially decoupled, and you don't get mixed orders of derivatives in the conditions. However, from fourth order onwards, decoupling them gives rise to very, very weak necessary optimality conditions. And we have an example, a polynomial example, where you can look at what is the fourth order condition implied by this theorem I just stated. And you can see here on the slide that you have second derivatives, third derivatives, and fourth derivatives in it. And though by appropriate choices of S1 and S2 directions, you can imply that the fourth order derivative is non-negative on the intersection of the kernels of lower order derivatives, this is very weak by comparison. So from fourth order onwards, we cannot do what we did for ARP. And I don't, trying to do these things, using these kind of conditions in the algorithm seems very involved. So the question is, what is a good measure? What is a good optimality measure for qth order criticality so that we can use it in the algorithms and we can analyze it? The idea is that one can come up with a conceptual measure that is computationally expensive potentially, but that allows us to perform a complexity analysis and to give bounds, and that actually, at least in the cases we know, reduces to known measures. So let me get to it. So the measure looks at the largest possible change in the Taylor series of F up to order J, in the jth order Taylor expansion, in a ball around the current point X, a ball of size delta. So notice this very theoretical assumption that you have to do global minimization over a ball of this polynomial, or Taylor polynomial. Okay, so, but it's also a stable, and we can give some measure of stability that the function doesn't change much if you look at this notion around such a point X, critical point, then it's a robust notion of criticality. In a moment, sorry, I have not defined it yet. I'm jumping ahead here a little bit. So take this phi delta that describes the largest change in a Taylor in the jth order Taylor model in a ball of size delta around the current point X. It's a continuous measure. When you look at J being 1, this is just a multiple of the norm of the gradient. If you look at the second order phi, this is a multiple of the smallest eigenvalue of the Hessian in absolute value when you care about it. So notice that if delta is 1, these measures are the same as we had before for first and second order. Exactly. When for third order, there is also a good enough correspondence, not quite perfect, but good enough. So what is our theorem here? That if X is a local minimizer of F, then up to qth order, this ratio here of phi delta over delta to power J converges to 0 with delta. So and it implies these complicated expansions we had before. So it's a necessary condition. So phi delta over delta to J is being small or being 0 is a necessary optimality condition for a minimizer. And so you can see here that we recover earlier conditions. It implies the complicated one, and it has quite a compact form at the expense of having to do this kind of global minimization to calculate phi. So indeed, now I will describe a regularization method, an extension of ARqp that incorporates phi as optimality measure. And so we also have to incorporate it for the model decrease. Okay, so here is ARqp, and you can, again in red, I've included the changes to before. So what we have now is that we have a value q less than p that will be the criticality order that we want to certify. The model is just like before. And then what we have to do when we compute the step is we also have to compute a radius for the optimality. So we have to compute a delta S to find it somehow, such that we have the same condition as before, but we have that the phi for the model is decreased to order epsilon j times delta j. So you can see here the optimality from before for the model is phi of the model over delta to power j. So we are making that small. for j 1 to q. So that's the condition in the model. We measure progress just as the same as before. And then we have to say a little bit what we do with this delta. Well, if we take the step, then we change the delta. Otherwise, we stay at the same point and keep delta unchanged. The sigma changes the same as before. The regularization parameter changes the same as before. There was a raised hand.
Yeah, I want to ask you how to do the second step conveniently. Can you elaborate a little on this step?
Not very much, but one can imagine similar. You can think of trying a delta, for example, starting with the delta 1. That's the ideal choice. So you can start with delta 1 and then kind of shrink it. So a kind of a backtracking strategy until you get the condition satisfied. Okay, so something like this. And what we can show is that there is a multiple of epsilon j such that once delta gets below that value, you can satisfy these conditions. So you know that actually delta varies between between a multiple of epsilon, think of epsilon as smaller than 1, and 1. So, but that's multiple of epsilon depends on Lipschitz constants, all right? So you know that there is a good interval there. And so one can imagine kind of a backtracking strategy. I'm not claiming these things are cheap, okay? Experience from trust region where one can do these kind of things, but here, of course, it's harder because of the higher order. But just bear with me on this conceptual trip to see what we can do with these models.
Okay, thank you.
Okay, so we can give a complexity bound. We are going to terminate. So I have a stronger requirement than in ARP. In ARP, we only needed Lipschitz continuous derivative of order p. Here, we need all Lipschitz continuous from order 1 to p. In fact, what we need is the boundedness of the derivatives and the piece order Lipschitz property. Okay, then I'm going to terminate this ARqp algorithm when phi of f is small, phi over delta to j is less than epsilon j for some delta. Okay, delta can always be 1 if q is 1 and 2. We'll see in a moment. This is just like in ARP. And we have to secure a delta of at least a multiple of epsilon for this framework to work. Now, if q is 1 or 2, so I just want to check what am I getting if I just want first and second order criticality. Well, then you can replace j in here by 1 or 2, and you get p plus 1 over p and p plus 1 over p minus 1. So you get exactly the bounds for ARP. So then you just recover with this framework the bounds for ARP. It's not surprising since the optimality measures coincides with known measures then. But if q is greater than 2, then this framework has this bound q p plus 1 over p. And it's again sharp. How is this bound? Comparing, so if I had here, instead of j, I had q, right? So I can put that's kind of the worst power there. So this p plus 1 over p minus q plus 1 would be a better bound than what we get here. So qp plus 1 over p is a bit weaker than what one would expect if one generalizes the sort of the known bound for ARP from order 1, 2. If one tries to extrapolate that to order q, then that would be kind of better than what we get here. However, the notion here, the notion in ARqp of optimality is a very strong notion because it's a robust notion. We are trying to secure a stable minimizer, essentially, over a ball around the current point. There's no change in up to qth order Taylor. Sketch of proof, same as before, but one of the steps is much harder. Sufficient decrease, same about as before, we do nothing else. But now we need to lower bound the step, and that is very, very challenging. What one has to do is what one gets from Lipschitz properties and boundedness properties is a bound here. This is getting very technical, I'm sorry. A polynomial in the norm of the step and delta. and then one derives a lower bound on the roots of this polynomial, and then one uses the lower bound on delta to secure that the step is like j over p. The worst j here is q, and hence putting these two together like before, we get the bound. And similar mechanisms for summing up over successful and counting unsuccessful steps. So just the lower bound on the step now is quite a lot more challenging, and we also have to have various proofs on the lower bound on delta, and proofs that actually the algorithm is well defined. Okay, so a few comments. I already hinted at the fact that if one tries to generalize, the bounds we had from first and second order, so this p plus 1 over p minus j plus 1 bound, if one tries to get that all the way to order q, then it is possible, but with a weaker notion of optimality that has just delta here, not delta to j. This is actually much weaker. We also have truss region methods, standard truss region methods up to order q, and the complexity there is epsilon j to minus q minus 1, which is worse than regularization method. So ARqp, that has complexity q over p plus 1 over p, that is better than the truss region bound, just as we've seen for comparing in general regularization methods with truss region and line search. We can incorporate convex constraints into ARP and ARqp without affecting the complexity bounds, but we have to solve the subproblem over the convex constraints using, say, projected iterates in a feasible way. Okay, how much time do I have?
Let's say 7 minutes.
7 minutes. Okay, I don't have much more. I wanted to just, it's more like an appendix a little bit. Let's assume we go back to ARP. Okay, I hope this is possible. So I want to drop the qth order. I just want to return to using a piece order model and just certifying first order criticality. So just a sufficiently small gradient. And I want to see if we can give up on the Lipschitz continuity assumption on the piece derivative. Can we relax that in a universal way? And can we also play around a little bit with the regularization power? Okay, so another variant of regularization methods. So this is trying to sort of take into consideration ideas from Yuri on universal methods, and from Grapilia and Nesterov as well. So universal ARP has a Taylor model TP and the regularization term to power R, where R is greater than P, strictly, okay? Then how do we decouple the ingredients in ARP? Well, the termination here, so I just want a small gradient, is it's the regularization power that comes in, so it's R minus 1, and here I have, I measure progress with respect to TP. All right, I update sigma as before, but I have to be more careful with the steps. So we have this condition that the steps are, in some sense, have just the right length, okay? Not too long, not too short. So we have this condition here on the length of the step, where alpha is a parameter I can choose at the start of the algorithm. Instead of epsilon 1, if you don't want an algorithm depending on epsilon, you can put the norm of the gradient at xk plus sk. So the universal ARP framework proceeds as ARP, but it's going to also enforce this condition on the step, and it's only going to allow the trial step to be accepted and possibly decrease the regularization parameter if this condition is satisfied. So the condition for a successful step is that you also have to enforce this condition. and have rho sufficiently large. So in that case, what can I apply this framework to? Well, I'm more careful with the step, and I can then apply regularization methods to a larger class of functions. And the class of functions is Holder continuous piece derivative with exponent beta p. Okay? So, sorry, instead of LP here, it should be L, sorry. So if beta is 0, so the Holder exponent is 0, this is just saying that the derivative is uniformly bounded. If beta p is between 0 and 1, the derivative is continuous but not differentiable. If beta is 1, then we have the usual, the piece derivative is Lipschitz continuous. Exponents larger than 1 are not much of interest because f then reduces to polynomials. So as you are aware, Holder continuity can be viewed as a bridging case between the smooth and non-smooth worlds. And in that case, what we have here is that choose the regular, so you have a piece, sorry, f has derivatives up to piece order. Beta p can be 0. And the regularization parameter is greater than p plus beta p, but beta p is at most 1. So you can choose the regularization to be p plus 1. So you know you have derivatives up to order p, choose the regularization to be p plus 1 or larger. There is not much benefit. It will not come into the complexity. But essentially, you don't know beta p, right? In practice, you're not going to know the exact smoothness of your landscape. It does not matter because the complexity naturally depends on the smoothness parameter without you knowing that smoothness parameter in the algorithm. So here's the complexity, depends on p, the order of the Taylor polynomial, depends on beta p, does not depend on the regularization power. And this is to drive the gradient below epsilon 1. So it's universal. It does not know beta p, but the complexity automatically inherits it. We do not use beta p in the algorithm at all. We don't try to estimate it. Okay. And just to maybe convince you that these landscapes can be quite non-smooth, here's a sharpness example just for first order. So here we are just plotting the difference in the gradients over a beta 1 between 0 and 1. So it's just it's plotting the Holder constant for a fixed beta. And you can see that it's barely looking smooth, okay? So it's looking quite ragged. So that's the end of my talk. Thank you for your attention.
So thank you, Cora. Thank you very much for a nice talk. So it is time for questions. Oh, we already have a question. So please unmute your mic and ask the question. Daniela Di Serafino.
Hi, Cora. Very nice talk. And I just was wondering, actually in your ARqp method, computing the high order regularization model and ensuring high order criticality is computationally expensive. Are you aware of any applications or examples where the better complexity bound that you obtain with ARqp balance the computational cost?
Not really. Yeah, this was a very much a mathematical exercise, but what I would say is that one would, for example, one could consider approximating, of course, third order derivatives by differences in Hessians or gradients, and we saw some of this in Yuri's talk. So then maybe some of these approaches become more tractable, more of interest. For example, Benedetta and Stefania, I will reference their work. They've looked at this with Philippe. at allowing more and more inexact approximations of derivatives. But we have not looked a lot at how to minimize this. But one can use anything, but what would be efficient to use?
You can also think of partially separable functions, though.
Indeed, indeed, indeed.
Okay, thanks a lot. I just was curious to know if you were also addressing this issue or if you plan to address it. Just a curiosity.
We have not in great detail, but separability, Philippe has looked some at separability.
Okay, thanks a lot.
So we have two questions from Valentin Borreco. So you can ask the questions, Mr. Borreco.
Yes, thank you. My questions are somewhat similar. I've seen there was recently a paper that's called the stochastic tensor method for non-convex optimization. It is based on your work, and I've seen it was also done with collaboration with you. And they said that for the future it would be nice to understand if it's how it would be better to compute tensor vector products and how to practically do it. And I wanted to ask you, do you know of if there is efficient implementation, let's put it like this, of tensor vector products? And sorry, and second question would be also very connected. This ROK, which is very important for adaptive regularized methods, would it be feasible in the stochastic setting when more or less for every batch one would need to compute the whole function? So
okay. Okay, so in answer to your first question, so I've seen some work of Ernesto Bergen and collaborators. So you know Ernesto Bergen?
No, I believe no.
So and Martinez, Bergen and Martinez. Sorry.
Thank you. Wait, I'll try to find it.
In Brazil. And they have looked at some of these fourth order models and implementations. I think there is a lot of scope for trying these things. In quite a few years ago, so there is older work on this actually. Yes. Also Schnabel. So if you look, for example, in the universal regularization paper, you can see in the bibliography, I've tried to find all the references I could to tensor methods, and there have been some more applied proposals earlier.
Great.
Not a lot, but some. So you could have a look there. Yes, there are a few recent methods. Also, Luki has had a paper. So yeah. And to answer your second question. So I'm a great believer in adaptivity, and this is one kind of direction that we've been trying also with Katja Scheinberg and Frank Curtis. You know, we are all kind of trying to convince people, also in the machine learning setting, that allowing this kind of adapting parameters in algorithms is beneficial. So there is more numerical evidence on machine learning applications that this can be beneficial, rather than what people do, which is to do a lot of tuning, a priori tuning, at huge computational expense, and with no guarantee really that when you try this on a new problem, when you try this on the testing data, that you would actually make progress or be guaranteed to converge. So the idea would be to try to replace this expensive pre-tuning phase with more kind of adaptive variants.
Thank you. But just the question is how to do this adaptivity in the stochastic setting? Because if for every batch one would need to, for example, compute to do one or two function evaluations, it's very costly. Do you know of any approximation of it?
So if you look at, for example, we have some papers with Katja where we look exactly at this with Katja Scheinberg. So we look, it's called stochastic trust region, Blanchett et al. And And there we look at exactly, you do some stochastic estimates of f that don't have to be very accurate. So you evaluate them, and in the algorithm, the assumption is that the evaluation in rho are independent of what you use to construct the model.
Yeah.
Then, but they can be inaccurate, and they can even be biased. Then you're still actually, you can have this adaptive framework allows you to kind of correct yourself, and it's a convergent framework.
Great, thank you a lot.
So thank you. There's another question on sufficient conditions. Please unmute your mic.
Thank you very much for the very nice talk. So I think there was in one of the slides some measure, and if some limit of it was 0, these corresponds to necessary conditions. I think it was before the ARqp.
Yeah, yeah.
Okay, so can you obtain sufficient conditions from this kind of analysis, perhaps requiring this to be positive or something like this?
So you can obtain sufficient conditions under the assumption that you can describe the region just with arcs. So, you know, just with kind of these arcs. Then I don't know if it's, you know what I mean. So we had this kind of arcs here, you know, x of alpha. So you have to, if your function decreases along curves that are not polynomial arcs, then it's very hard to say something. But if it only can decrease along arcs, then you can say that if you know, these conditions strictly don't are satisfied strictly, then you have a sufficient minimizer. So I refer you to the papers, to this paper in the Journal of Foundations of Computational Maths. So a lot of this paper is just devoted to these conditions and phi and so on. So I think it's I point you to that paper.
Thank you. So the idea more or less is that if you only have decrease through polynomial paths, then you can also
you can derive. Yes, you can derive sufficiency. Yes.
Okay. Thank you very much.
Thank you. Are there further questions? So then let us stop here, Cora. Thank you very much for a nice talk. Thank you, for answering the questions. So we had a nice discussion. And I'd like to announce the audience that we will post the video and the slides on the website of our seminar. If you get the slides, Cora. Yes. Okay, from you. And then I would like to thank all the speakers, the 15 speakers we had in the first season of our seminar, for great talks, for being a fantastic replacement, for conferences and workshops. And I'd like to thank the audience for being here every week in the last 15 weeks. So there will be a summer break, and we will meet again on September 7th with the talk of Amir Beck from Tel Aviv. Have a nice summer. Thank you very much. And stay healthy, and see you in September. Thank you, Radu. It was great to. Thank you to all the speakers. Thank you. And see you. It's time to go to the beach. Indeed.